So I guess my talk is not necessarily particularly succinct. I went for the idea of cramming a whole load of ideas into a talk so I can get some feedback or comments rather than doing something very specific and succinct. And it's sort of in three parts. I'm going to talk a little bit about my experience of mapping, because we're in the kind of teaching and learning track, but mainly I'm going to be talking about learning, or my attempts at trying to learn what a map is. Mostly the middle part is kind of a random assortment of things, stroke observations, which hopefully will spark other people's thinking or highlight things, I guess, that I don't understand potentially, and then people can teach me something, again, appropriate for the track. And then the last part is, I guess, focused on some work to try and understand bits of the map in a bit more detail. Very briefly, in terms of my background, because I think it puts some of the things I'm going to talk about in context. 3 days a week, I work in the strategy group for a law firm called Mishcon de Reya. But I teach in School of Management at a couple of institutions, and I guess I've founded, started a couple of companies. So quite a weird mix of things. And I guess I think they all impinge on mapping, or my experience of mapping, in slightly different ways. And I guess in the context of the things I'm going to talk about at the back end of the talk, or the end of it, my PhD is in computer vision. So, very very directly sort of linked to real mapping, as it were, or photogrammetry, and trying to interpret things in scenes and building models to interpret things in scenes. So I guess that's the background. Starting off, art and science of mapping. I guess we've been doing it for quite a long time. I don't really know a detailed history of mapping, but this picture is actually carved in stone from the 11th century. This is a map of China, and the first sort of cartographic grid that I can find. And the idea of the cartographic grid's gone back to the sort of 2nd century AD. So it's suffice to say that humans have been trying to map stuff for quite a long period of time. And in the context of what I'm going to talk about later as well, they aren't necessarily simple, right? So this is a kind of random nautical chart showing all sorts of things overlaid. And I guess the thing about maps is, although the framework that Simon has put together is very generic and very useful and can be very simple, I think its sort of natural conclusion or trajectory is one of more complicated maps with more layers. And I think getting the expertise in using it as an artifact and therefore being able to layer more information onto a map, obviously over time improves their utility. And we're at a peculiar stage where not many people know how to read a map or make use of one, and therefore progress is slow. But I'm hoping that progress will improve a little bit. And I guess I've been teaching it possibly for 4 years now. I don't know exactly, maybe even 5. Can't really remember when the first time I had a go at teaching someone to map. And I've been lucky enough that Simon has come and given me a few lectures to my classes as well. So I've learned a little bit about how to try and communicate it. I wouldn't suggest that I'm particularly good at it. And you can see from the slide deck here, this is a kind of outtake from one course I teach on designing kind of data-enabled businesses. Some of those slides will be very familiar to you, to those of you that have read the book, and you can see they're all sort of intermingled and smattered with other lecture slides and annotations. And so I kind of melded mapping quite deeply into most of the stuff I do now, actually, in one way, shape, or form. And I guess I've taught it. I say to teach in a very loose sense, because I feel like I'm just telling people what I know during the process of learning how to do it. But I've been doing it in sort of classes of 60 or so, mainly with MBA students, and it's very interesting, getting how people have different takes on it over year after year. I think I've got a bit better at teaching it, but not particularly. I still think got a lot to learn, and I really enjoyed Ben's online course, actually starting with the pen as a sort of a learning aid. I think I might try and pick up some of that. But I should say I've been using it day in, day out for quite a long time, and as a way to communicate ideas to people, I found it very, very useful. I particularly find it useful for working with founders, because a founder of a business really does understand, at least in their head, already has a mental model of the landscape and what they're trying to do. I found it harder to teach executive teams where they've kind of got an understanding of one part of the business, but not the rest of it. And I find it quite difficult teaching students who don't come with a specific business that they want to frame their learning around, because it's very difficult to get started if you don't understand a kind of vanilla version of a map. And then I guess I've used it for lots and lots of things. So this is like looking at machine learning loops. So the different stages of a data set as it evolves, and the different stages of an engine as you train it and deploy it. And again, I think that one of my learnings has been that the map itself, where you've kind of got evolution or maturation on the x-axis and some sort of dependency on the y-axis, is such a generic framework to think of things. I find it very difficult to unsee it in any meaningful way these days. And almost everything I look at is some sort of version of a map. And lots of the time I use it, I guess as a way of explaining things to myself as much as anything. I haven't done masses and masses of strategy on a map, probably a strategy novice in that sense. And because it's not diffused particularly well at the moment, I often find explaining strategy to people on a map, where you have to spend most of your time explaining what a map is, doesn't work particularly well. So although I've used maps on quite detailed projects, this is an example of a project for transacting UK title deeds on a blockchain with the land registry. The reality is that most of the maps I draw in the context of the strategy work I do don't actually see the light of day, so they don't appear anywhere, for better or worse. Like, again, I think over time that sort of thing is likely to change as more people understand what they're looking at. So maps as models. Oops, I realise I'm not keeping an eye on the chat. Hopefully there isn't any. Perfect. Maps as models. I guess I approach this from a couple, the background of, like I said, someone with background in vision for at least some of the time. And there's sort of two main things that I think are really interesting with a Wardley map as a representation of a business, for the sake of argument, but of a dynamical system. One is obviously the space itself. So the fact that it has axes, and in Simon's parlance, an anchor, but it has an order, or the space is ordinal in some sense, is very, very useful, and is different from a whole load of other things. And then the sort of heavy lifting of this dependency graph that sits in an embedded space is very useful, because both of these things we understand in lots of detail and use all over the place in other contexts. And as soon as you kind of see it, of having a dependency graph in an ordinal or a metric space, I think I sort of think, like, how could you ever have modeled a business any other way? And maybe I'll say just a little bit about what that means. First is spaces. So we're very used to thinking about spaces and projections of spaces. We sort of learn, perspective geometry at a fairly early age, and everyone's notion of a map is a kind of a world map. And the first thing to notice when you, at least to my mind, when you think about the artifact of mapping, is obviously the map itself has a whole load of assumptions in it, and you can see on the right-hand side a whole load of different projections, and those projections are representational choices and have biases. So the classic example is, the way the Mercator projection deals with area, such that, Africa appears comparatively small on the Mercator projection, but is in fact giant. I always find this is a useful way to illustrate to people that don't or haven't thought very much about mapping what the biases in maps are capable of doing when it comes to portraying information. But projections in general are used all over the place. Here, this being a projection, because we're taking a 3D version of the world and turning it into a 2D version of the world. And we use them all over the place in machine learning for kind of reducing or simplifying representations. So on the left-hand side, you've got a 3-dimensional space, and on the right-hand side, you've got a 2-dimensional space, and you use it for trying to simplify the representation of the underlying data before you try and build a model of it. The projection one is the one that you're familiar with from a sort of conventional map, but there are at least 2 other generic types of methods for thinking about spaces. The second one is kind of kernel methods, where we sort of do the opposite. We go, if in a projection set of methods, we go from a high dimensional space to a low dimensional space. In a kernel methods, we go from a low dimensional space into a higher dimensional space, again, to try and simplify the making of the model. And then the third one is kind of manifold methods or embeddings, where we try and we recognize that the data that we're trying to model is in a high dimensional space, and we try and find a low dimensional space, again, that captures or characterizes the type of problem we're trying to solve. So here, we're trying to, in this kind of toy example, we've got a Swiss roll model that in the original space means that the colors that are nearby in the original space are counterintuitive, because we think they should be far apart if it was kind of going to obey the kind of order of a spectrum. And there's a question about trying to learn a space that has the right representation. So when I see like maps as kind of low dimensional surfaces, that's the first part of Simon's framework that kind of jumps off the page. And then the second one is data structure itself, as being a directed graph. And again, we use graphs all over the place. And they're very well understood, for several hundred years. So the notions of stocks and flows, which obviously you come across in operations, and Simon talks a little bit about, but also weights and paths and cuts and cliques and colorings and duals. These are all kind of well understood, techniques or mathematical representations for dealing with or solving problems on graphs. And so again, suddenly, if you've got a business model that has a space, and we'll come back to whether it's what type of space it is, and it has a graph inside it, then suddenly you've got several hundred years worth of machinery at your fingertips to start making models with, for want of a better word. So I guess those are the first, although I kind of teach it, and you can see from the pictures at the front, the point of them being there was that, sit there with the whiteboard and scribble on it and iterate and work with people. I think most of the time I'm looking at these things, I'm thinking about all of the potential machinery that could lie behind, improving and iterating it as a model. So briefly, these are kind of random comments and things that I think are interesting and are supposed to stimulate thinking or dialogue. So the first one is this kind of idea of the y-axis. And although Simon talks about visibility a lot, because it's framed in the context of kind of business setting, like if you read, I guess, starting sort of philosophy of science type literature, I think you can order, nominally sort of causal ordering of things. And the one I like at the moment is this kind of purposes to principles to phenomena by Brian Arthur, thinking about how we build systems that satisfy needs, which obviously sits very well with this framework. And the second bit that I find useful is thinking rather than about individual components, but thinking as assemblies of components. And most of the time, the patterns we're interested in on the map aren't individual components. They're the co-evolution of sets of components. And Simon talks quite a lot in the online book about sort of co-evolution of practice. But I think there's quite a lot of work to be done on co-evolution of technologies, full stop. We'll come back to maybe what we mean by technologies. So, for example, the things we're interested in is not just how a single component moves on where we've got it sort of individual components on the right-hand side, but how sets of components move and how the inertial forces or the vector field that component moves in interact with each other and how they move over time. And I think one of the really interesting things on the map is how time is essentially normalized on a component level differently. So in Simon's sort of conventional version of the map, you've got time that is normalized over the maturity of the component on the x-axis, and every component moves in its own way towards its inevitable death that took further to the right than it started. And so I think I've thought a little bit about sets of components. And I guess another thing, these are just intuitions as much as anything, but you can see in this framework how, as things evolve, you kind of got standard business plays or standard business moves. So think about kind of move making and move minimization as an optimization framework. Things like, price volume curve, solution improvement should play out as kind of microstructures on a map, and you should be able to enumerate and model the moves that businesses make. And then I think there's another thing that's kind of interesting at a macro scale around kind of investment fields, which is how do sets of components in a business move, and how does a very high level strategy affect that. And there's quite a nice paper by Gans and Stern, which I think is called the entrepreneurial compass, and is nothing like a compass, because most of what they're talking about doesn't have this property of being in an ordinal space or a metric space. And so I think when I think about Wardley mapping, I think a lot about how to frame existing problems that have been addressed and just draw a picture of them, which is, to my mind, amazing. I'm going to turn the light on. It's getting a bit dark here. Big dark in London. Second things is flows. Although there's all sorts of interesting flows. This is a kind of mock-up of Simon's T example, but done as a P&L. So in the context of a business, there are different capital flows. Some of the capital flows in businesses are very well understood, and some of them are very poorly understood. Some of them are measurable, some of them are difficult to measure. But again, it's such a useful way to think about the structure. And I think the main thing that I like is this kind of separation of flows. So Simon often talks about evolutionary flow in the x-axis. But I think the sort of two-dimensional version of the map captures exploitation and exploration that you see all the time in business literature. And maximizing Y flow capital is exploitation, and maximizing X flow capital is exploration. And again, it fits very nicely when you think about transitions from A to B. And in another kind of analogy to another line of work, up here we've got a Feynman diagram from physics, which basically says you've got one set of particles on the right-hand side, and there is an exchange or a transition of energy, and you've got some particles on the right-hand side, and they're sort of pioneered to as a way of communicating structural change. And again, inside the map here, I've definitely put time in there as opposed to evolution, but I think it's the map, or this kind of X flow and Y flow, is a really intuitive way for people to understand the structure of investments and structure, are your investments maximizing, Y or X flows? Then when I think about the patterns, there's lots of things. Obviously, there's tons that Simon goes through in the book itself, but the notion of higher order components and the structure of higher order components enabling you to satisfy needs in new ways is useful. The notion in which an individual component can kind of move through phases. So I guess Simon focuses on sort of 4 stages of capital, but they are very generic in that sense that you can think about them as enabling. So on the far right, you've got a component that's green, maturing and enabling a new component that's blue, and that's very again very general. Let me just read Philip's comment. I don't totally understand that in real time. I'm not very good at reading. I'll come back to it. I think frame it as a question at the end, possibly. Again, the beginning. Sorry, pretty slow. I probably use up 5 minutes just trying to understand what you were saying. Like another thing that I wrote a short blog on, but is an interesting one, is kind of structural deepening. So not just the individual components mature along the x-axis, but that structures of components mature, and in general there are probably lots of patterns that you can see baked in. So here the structural deepening pattern, again this is kind of from Arthur, is that as a system matures, the number of subcomponents that go into satisfying the purpose that's being met increases. So those are kind of high level things that if you think coherently about the structure of assemblies, you get into thinking about co-evolution curves and why does one technology replace another. And this is some work by, where have I put it? This is by Adner and Kapoor, where they're mapping. I mean, these are my diagrams, but if you go to the original text, they're mapping the evolution of lithography technologies and why certain ones hit the market and changed and certain ones didn't. And you can come up with, again, sort of mapping it in a Wardley sense, these different types of co-evolution curves. So where 2 technologies can coexist for a long period of time versus where you get something like creative destruction because the two co-evolution curves coincide in a certain way. And again, I think there's lots of things where you can take an existing body of literature and reframe it in a much more intuitive way using a map as a framework. Simple models, given that it's a very generic framework, like a graph in a space, I think there's something useful to be done with really simple models. Again, this is a paper by Arthur, but showing essentially a kind of evolutionary simulation of the design of a computer chip. And so things I've been mucking around with in the context of a Wardley map are with neural networks. So neural network takes an input, converts it into an output using by learning, quote unquote, a mapping function. And a lot of the state of the art is in kind of neural architecture search. So essentially trying to find architectures that produce good results, and to do so by evolving them against a series of tests, which you might as well think of as needs, and altering them. And so I started to play around with, I'll skip forward and come back. I started to play around with, Wardley maps of neural networks. So this is an NLP network on the Penn tree bank data set. And so you've got a neural network at stage 50 and a neural network at stage 12,000, and they're essentially evolving. So this is how it would be commonly discussed in terms of the structure or architecture, and this is how you can start to think about it. And thinking about a Wardley map of a simple, quote unquote, deterministic system, I think would start to give us useful insight into the types of patterns and behaviors that we might want to see when we look at a Wardley map of a much more complex system where we can't measure it in the ways we might want to. This is kind of before and after. So of all those things that I think are interesting, what have I decided to spend my time doing at the moment? Mostly trying to construct a kind of a real map from data. With limited success, and to a certain extent this is a teaser because Simon has giving me the opportunity to talk at MapCamp in October, when I'm going to have much better results, hopefully. So this is a little bit of showing you work in progress. But the thing that's interesting to me from Simon's framework is the idea of using text, or using a document to measure the progress of the evolution in a space. So the one that kind of always gave me the cold shiver, or the realization moment, was when I kind of got to this part where we had the probability of an event being more likely and less likely depending on the stage of maturity. And this kind of the diagram on the left, using text in the description of the artifact as being a way to measure it. And I still think this is probably the most important aspect of this whole framework. Obviously, we've talked a lot of the talks been a lot around strategy cycles and context awareness, etc. But the notion in which you can use the description of an artifact to position it in a space, I think is awesome. So I've been thinking a bit about that. And there is some precedent for it. So this is John Stearman, who's a professor at MIT, thinking about simulation models for scientific change. So things like, Kuhn's notion of, normal, science, and crisis. And you should be able to see patterns of these behaviors in the literature when it comes to a technology. So what sort of things are we looking for? This is the kind of state of the art. So this is 12,000 papers looking at HCI and mapping how they fit together. And it has all of the problems that Simon alludes to. So it's got, it's got a graph. This one's been done with latent Dirichlet allocation that tries to understand the structural interconnected of components, but it doesn't deal with the evolution, and it doesn't put it in a space that means you can make any useful inferences about its future evolution. Even if we get into the structure of citations, again, the literature is full of these things called maps that aren't maps, and I think that is a useful thing to focus on short term. And so if I think about Simon's larger framework, I haven't got all the way holistically through all the stages of capital. Where I'm tinkering around at the moment is very much in mapping the genesis stage in detail. But I think you can do it. You can start to do it quite convincingly. So here you've got, this is just an illustration of a corpus that's built up over time. And in the structure of the corpus, you've got different kind of properties. So you've got highly connected kind of small world nodes around, literature review papers that put other work in context. And really, you've got innumerable papers. So, part of the interesting thing is, how do you do this? If you're estimating a field with a document, how do you get an accurate representation of the field? We need a lot of documents, which means you kind of need to automate the process, and you need to be able to transfer knowledge from the sample you look at to the rest of the sample. And so I've started to do a bit of work on trying to, with a load of other people as well, on how to do this. And the interesting thing is, I'll come back to those. The interesting thing is that language models have come on dramatically in the last 2 years. So can we build kind of machine learning / AI systems to understand language? And if you tried to do this 5 years ago, the answer would probably have been no. But this is benchmark performance on standard NLP data sets in the last 18 months or so. And if you look at the diagram, the graph on the right, you can see a dotted red line, which is human performance. So if you define the language task narrowly enough, you can now basically get human level performance on automated interpretation of text, which is kind of a weird period to be living through, the consequences of which I'm not totally certain of yet, but it is enabling potentially us to do more systematic review and model building from text, which is the kind of the key component. And the main driver from this is these things called pre-trained massive models, where you can learn a neural network in an unsupervised setting and train it on millions of documents, like training it on Wikipedia or the Common Crawl, and then you can adapt that grammar that is learned in the deep neural network for a specific task. So I can take a language model that's trained on the whole of the internet, for the sake of argument, and I can then turn it to, can I identify certain type of text or certain types of references to measuring the components as they evolve. And so this is an example data set of the sorts of things we started to construct. This is looking at the evolution of blockchain. But we're building up some labeled data sets so that you can start to project a taxonomy or even learn a taxonomy from a set of literature. And so I guess the idea is that you would be able to learn a space where the map that produced a map that was useful as a starting point for thinking about other things. So this idea of learning taxonomies is a component, is at stage T, and as it matures, it is related to other components that indeed at some point mature to the point where you can recognize them from a corpus based on their citation models. Like I said, I'm working at the moment right down in the genesis stage where, for example, the structure of the corpus is richer and more dense than it would be perhaps at later stages of capital in Simon's full model. And I think the interesting thing about when you model this is time is sort of normalized in both X and Y, because you can see that intuitively by you know that X is normalized because the life cycle of the component is all on the graph from left to right. You notice that I've removed the arrows because I don't think these things work like we normally think of axes. They're kind of absolute rather than relative. But actually, because you've got higher order components that are dependent on a pre-existing component inside a kind of causal model, time is also implicitly normalized on the y-axis as well. Like things appear up and to the left as you would get from a normal kind of Wardley map, and then they sink or swim depending on whether they get picked up and proved to have utility. And so I've stopped using time or time hat or time bar because it just gets really, really confusing. So I've started splitting these kind of two Chinese radicals as a notion of split axes. But the idea here is that a paper referencing a technology, and here you can think of a document as a measurement process for the state of the evolution of the technology. So the way people write about the technology is a measurement process for their perceived view of how that technology is in the world, and citation graphs linked together. So as one representation of the technology matures, it gets more citations, and that kind of lifts it and holds it up. And you should be able to group sets of citations around the maturation of a single component. And then as these things evolve, new componentry emerges, and the dependency between componentry is also sort of picked up and used. So those are the sorts of things I'm trying to work on a little bit, and it's essentially how do you use a document as a point measurement of a vector field of some description, where technologies in principle are moving through the field and are being influenced by the movement of other things through the field. But it's very odd because any component on the map is being normalized, being normalized on an individual basis and against all the other ones moving around it. So it behaves it behaves intuitively like you'd expect a Wardley map to behave. But given that we're not used to looking at Wardley maps of dynamical systems, then it's kind of weird to get your head around at the beginning. And I guess what I foresee, there's more comments, sorry. Yes, yeah, basically, I think that is where we'll get to. So this is an example from a DeepMind paper in Nature of the mapping of a state space of an algorithm for playing a game. And we can map a state space or we can map a strategy space in a game because we know everything about the state space of the system. And the question is whether the measurement methods that Simon alludes to around thinking about the way things are reported could ever get a high enough granularity or fidelity of measurement to make a computational strategy space useful. But I guess my intuition stroke hope is that is the case. And perhaps we can talk about that later on what's good or not good about that. So in summary, I really like Wardley maps. Everyone that knows me well enough knows I never shut up about them, for better or worse. And like I said, after I saw it, the first time I saw Wardley map, I must have, like, after 3 minutes or 4 minutes or something, gone, there we go. This is a missing piece of the jigsaw puzzle. I think the machinery that is built around maps is very, very versatile. We've got hundreds of years of understanding this kind of mathematical machinery. So I'm hoping that we can, make some progress. Maps are a certain type of model, and I feel like there is a ton of work to be done. There we go. These are my kind of mapping workflows at the moment. I won't go into them. They might be useful, but I tend to think of separating data sources from representation from the rendering, and most of what we think of as the map at the moment is just the kind of rendering process at the end. I guess I also have got completely fed up drawing maps. So in principle, you can sort of auto-generate them, and I've put some LaTeX stuff up there for people if you want to use it. But I realize that LaTeX is definitely not everyone's kettle of fish. So there you go. That was my whistle-stop tour of learning and teaching Wardley mapping. As you can see, there is a lot of stuff that I don't really understand or know, but I feel like I'm making incremental progress on some of it. Thank you very much. Questions or discussion or not, as the case may be. Thank you very much. Yeah, whistle-stop tour. I should say, prior to doing computer science, I did quite a lot of philosophy and history of science. If you look at the library, it's probably half philosophy of technology and history of science. So there's a lot. I think a Wardley map is such a concise way to think about a vast number of interesting topics. Like Kuhnian notion of paradigm shift, how you measure evolution in systems. Like if I spent this morning, I don't know where it is now, was in front of me. I've been reading quite a lot on how you measure history of the Earth, so structure of sediments and things like that, which I think have got applications here. Question: your Wardley maps seem to have been almost logarithmic x-axis, more lines at the end and the middle. Can you explain the semantics of that? Yeah, I mean, it's just from Simon's. I'd never heard Simon say that he uses a log axis, but it's very clear that he does use a log axis. And you're basically compressing, because you're interested in the now, but you're interested in the influence of the distant past and the immediate present on the components that are mature enough to make up the mechanisms that satisfy your needs, right? So you let me pick one that's got it in X and Y. So you can see that Simon's shading is logarithmic in that sense, right? Because things are, if you ignore the left-hand side, things on the right-hand side could have been around, for quote unquote forever. So components, as they go through the commoditization phase, for example, they kind of stack up if they don't die. Like if you look at the mechanisms of death in a Wardley map are quite interesting, which is like how do they disappear and produce technology strata at the bottom. I haven't got that picture in there. I will make certain I talk about that the next time a little bit. But what I was going to do, depending on getting Simon's feedback on this talk, stroke permission, I was going to go through the normalization process that you're seeing here in more detail. Sorry, more questions. Oh. No more questions. Just people talking. Yes, I mean, so I've always thought, I don't know whether the shading was deliberately logarithmic, but it makes a lot of sense for it to be logarithmic, because you want to, the stable part of your evolving system is the stuff in the middle, so to speak, and the very unknown stroke less relevant stuff ends up in at the periphery, and so you end up with it sort of works on the y-axis a little bit like that as well, which is that you want to, when it comes to visualization, you want to bias the focus of attention to the structures in the middle effectively. You can imagine if you didn't logarithmically compress it, then large bits of history that underlie your componentry would take up large proportions of the map, and most of the map would end up being kind of static, stable, and irrelevant. So from using it as a way to understand strategy in an evolving system, you always want the most stable, for example, and the least stable bits of the map to be minimized, so you can concentrate on the stuff you can do something about in the middle. Going back to some of the, I thought Ben's talk on tactical timeframes, tactical and strategic timeframes is kind of important. And you can imagine, having Wardley. The reference frame for Wardley map is application specific, is task specific in that sense, and framing it for strategy versus tactics. You can imagine, being able to recompute it in some meaningful way. Cool. Okay, I think, is it next talks yet? Nearly. I'm happy to hang on, but I was going to catch practice of mapping talk directly after this. So, is there a third dimension to a Wardley map? Yeah, like in the, I think the whole dimensionality thing is a misnomer. Like, we use 2 dimensions to make things representable, but really a Wardley, if you think of the vector space that the text is in is massively high dimensional, and so if you think of the Wardley map as being one particular projection method into a low dimensional space so that you can use it as a map, then yes, there are as many dimensions to the map as you want, but obviously humans get much worse at reasoning in high dimensional spaces. Well, not obviously, but they do. Empirically, people aren't very good at reasoning in high dimensional spaces, and therefore most of the things that we use are low dimensional representations of things. Oh,
hello.
Hello. There you go.
Hey. No, not at all. First of all, massive apologies, because there's so many good sessions. I want another session. I came and joined this one, so I missed a bit at the beginning. You were talking about the logarithmic. Well, the axis and the x-axis actually comes from that ubiquity certainty curve, and you're absolutely right. In order to do that ubiquity certainty curve, the actual axes are logs. In terms of the shading, because I just caught the very end, so I may be misinterpreting what you're saying. Certainly, there will be compression at the ends. I mean, it's the only way. God, it was so many accidents upon accidents. I mean, the worrying thing is people look at the maps, and the real effort was in that axis at the bottom, and people will think that somehow I managed to think my way there. It was a whole bunch of random accidents after accidents, which led to that whole evolution curve, which led to that axis. Am I completely missing the point?
No, not at all. Yeah, I mean, if you take empirical data and you start plotting the you're essentially normalizing your x-axis, it all becomes clear, quote unquote.
Oh, right. Well, I'm going to have to watch the video afterwards. I'm so sorry I missed the beginning of this. Again, I started with Alex and wanted to come and join this later, and so I will have to watch it. But I did hear you say, if Simon gives me permission, whatever you wish to do, you have permission. Oh, don't wait for me. God, all I did was open a little doorway and say, look, there's something about situational awareness that it's going to take others to walk through and actually make this field into, my maps are so primitive. Someone's going to make way better versions.
Well, yeah, I think we're well on the way, so to speak.
Good.
I mean, it's good fun.
Good.
The more you learn, the more you realise you don't understand it.
Well, anyway, so there was a lot of the evolution axis is particularly interesting and fraught with. I still remember 9,223 publications approximately went into the analysis of those. And that through random experiments eventually led to that axis. But here we are. Okay.
Very good. Thank you, everyone. I'm going to go and see another talk, if that's okay.
Pleasure. Thank you.
Speak later. Bye.